Happy Monday! Welcome back. This is our last lesson that we're going to be doing on probability, and then we're going to be doing an actually slightly different way of assessing what we've learned on Wednesday. So it's not going to be a Delta Math, but it will be just kind of going over everything we've learned. So today we're going to be looking at independent events, what that means, the formulas that we use with that, and how to determine if two events are independent. So just the beginning of it, I'm going to review some things that we looked at before. So the first thing, you want to take notes on all of this. If A and B are independent events, then, and remember that this is red, the probability of A given B would be equal to the probability of A, meaning that the probability of A is the same whether or not B happened. Okay, so they're independent, so it's not affected by whatever B is. Also, the probability of B given A is equal to the probability of B, meaning that the probability of B is the same whether or not A happened. Okay, so this is why we're allowed to say that the probability of A and B equals the probability of A times the probability of B only when the two events are independent. Take a second to write down that and everything that's in our table right here, because this box. This box right here are going to be the formulas that we're going to be using to determine independence, if two events are independent. So while you're writing that down, I'm just going to talk for a second. And the basic idea of independence is, in this example, remember when we talked about rolling a dice and tossing a coin? So if I have a dice, my beautiful little drawing of a dice, and I have a coin, okay, what's the probability that I would roll a 2 and get a head, right? So if I roll the dice, the probability that I get a 2 is 1 out of 6, and the probability that when I toss the coin, it would be 1 out of 2. Whether or not I get that 2, whether or not that 2 shows up on the die, does not affect what happens with the coin. So the two events are independent. They don't affect each other. That's why we're allowed to just multiply these together, and that tells us the probability of both happening, okay? So I'm going to erase this, but feel free to pause and write that down if you want to understand when two things are independent. So these are independent events, right? Because whatever happens with the dice does not affect the coin, and the coin does not affect the dice. It's going to be that way no matter what. Okay, just to not overwhelm what we have written here. All right, so what does it mean for two events to be independent or dependent? Okay. Miss Moody has a bag of Swedish fish that have mixed colors. There's green, red, and yellow. I got rid of the orange. And there's no orange. Okay. There's 5 green fish, 8 yellow fish, and 10 red fish. I put them out here. Here's the bag that Miss Moody has. First, we want to say, what's the probability that she randomly pulls out a yellow fish, decides that she doesn't like it, puts it back in the bag, and then pulls out a red fish? So let's see what would happen. So what's the probability that if she reaches her hand into this bag, right? Here's all the stuff that's in the bag. She reaches her hand into that bag, and she randomly pulls out a yellow fish. What's that probability? Well, how many yellow fish are there? So first we have to see how many yellow there are, and we know that there's 8 yellow, and then we have to say how many total fish are there. So we count all the fish, and there's 10, 18, 19, 20, 22, 23. Okay, so that's the probability that she would get a yellow fish on her first pick. Now, she pulls it out, but what does she do with it? She says, ooh, I don't like yellow, and she puts it back in, because who really likes yellow Swedish fish? I like the red ones. Now she's going to reach in again. What's the probability that she gets a red fish right now? So now we want to get a red fish. Well, how many red are there? There's 10 red. And how many total are there? There's 23. Okay. Did the first event affect the second one? Let's think about this in a second. So we would multiply this together, and 8 times 10 would give us 80. And 23 times 23 would give us 529. Okay, let's look at B now. What's the probability that she randomly pulls out a red fish, eats it, and then pulls out a green fish? All right, so she reaches her hand in the bag, grabs a red fish, takes it out, but this time she likes red because red's delicious, and she eats it. So the probability that she pulled out a red that time, okay, there were 10 red, because this guy was here, so there were 10 red out of the 23 total. But now this guy is eaten, so he's no longer there. Now she reaches in and she's going to try to get a green fish. Well, how many green are there? There's 5 green. And how many fish are in here? There's only 22 fish now. Notice that the number of fish is less. So we would multiply this and we would get 50 over 506. Did what happened the first time affect the second time? It did. Because notice that what it was out of changed. That's like conditional probability. Okay? So our denominator changes. In this case, it didn't change. This is independent because the first event, we put it back in so everything stayed the same. So the first event did not affect the second event. Whereas here, this is dependent because the first event affected the second. So take a second and write it down for yourself, whatever way makes the most sense to you. Okay, I wouldn't copy this, all of this. Just explain what independent is and what dependent is in your own words. Okay. And now we're going to do it formulaically. Oh no. Oh wait. Oh, there it is. Okay. I thought I lost all of this. So the first thing is to determine, I don't know what this is. All right. To determine if two events are independent, you must prove that both these statements are true. So, and we said that here in the box, okay, that the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. So that's exactly what we would need to determine. Now remember that to find the probability of B given A, you find the probability of B and A divided by the probability of A. Okay? So remember that this is always because it's given that A happened, so A is our denominator. In this case, we would now find the probability, if we're finding the probability of A given B, the probability of A and B happening over the probability of B, because here we're in the world of B. And we want to see, is this equal to the probability of A? What this means, that the chance that if A, the probability of A happening would be equal to, so the same as, the probability of A given B. Meaning that given that B happened, what's the probability of A? If that's the same as the probability of A, then it doesn't matter that B happened. That's what independent is, because it doesn't matter if B happened, they're still going to be equal to each other. Okay. I would just write this formula down. You have it from the other day, so you don't really need to write it again. If you're just continuing your notes, you might want to just go back and highlight it because we're going to use that formula. Now let's look at some examples. Okay. Events, I would write this example down. Events A and B have probabilities. P of A equals 0.4. The probability of B equals 0.65. The probability of A or B happening is 0.85. So the first thing I want to do is find what's the probability of A and B, because that's going to be really important finding the given that's, right? So probability of A and B. So to find that, I'm going to use the formula that we just talked about, which is the probability of A or B is equal to the probability of A plus B minus the probability of A or B. And just as a little reminder where this is all coming from, if this is A and not A, and this is B and not B, okay, you're finding the probability of A or B. So that means anything in the A column, anything in the B column. So all we're doing is we're saying we're going to add the total probability of A, the total probability of B, but since this is in both of them, we're going to take it out so we don't count it twice, because it would be counted once here and once here. So we have to subtract that so that we don't count it twice, and that's the A and B. Okay? Just so you understand where this formula is coming from. So now we're going to plug in all of our numbers. So do we know A or B? Oh, I wrote this wrong. This one should be and B over here. My bad. Probability of A and B. Sorry about that. You might want to fix that. You definitely want to fix that. Okay. So we're going to plug in. Do we know the probability of A or B? We do. It's 0.85. The probability of A is 0.4. The probability of B is 0.65. We don't know the probability that A and B happened. So now we just simplify. So we can combine that. We get 1.05. Bring everything else down. Okay. And now we solve. So we subtract this from both sides. 0.85 minus 1.05 gives us negative, sorry that I'm going into here, 0.2 equals negative and B, and we just divide by negative. So that means that 0.2 is the probability of A and B happening. So that's going to be important. I'm just going to move that up here. Probability of A and, tonight is not my night, and B. Okay. Now, are the events A and B independent? So we have to use mathematics to justify our answer, and they ask this on the Regents all the time. So that means we're going to use the formula. So we want to say the probability of A given B, and we want to find the probability of A. If these two things are equal to each other, then it's independent. If they're not equal to each other, then it's dependent. Okay? So let's figure it out now. The probability of A and B. A given B. So we find the probability of A and B, and we divide that by the probability of B, because that's the world that we're living in. So the probability of A and B is 0.2 divided by the probability of B, which was given to us as 0.65. The probability of A was given to us as 0.4. Now all I have to do is see if these two things are equal. So I just divide this, and I get 0.3077. Okay, these are not equal. Therefore, these two events are dependent, meaning that whatever happened in one of them affects the other one. I'm going to now give you an example with actual events so that you can see. If you would find that they are equal, then you would want to do the other one to just make sure that both are equal. Okay? So let's do a second example. Pause this, write it down. When an avocado is selected at random from those delivered to a food store, the probability that it's ripe is 0.12. So if you've ever gone shopping and tried to buy avocados, if it's really, really hard, they're not ripe yet, so you can't eat them yet. If they're really soft, right, they're ripe. But if they get too soft, then they're bruised. Okay. And so we're going to start filling in information from this. So it tells me that the probability that it's ripe is 0.12. So I'm going to go to ripe, and that's 0.12. Since I'm working in probabilities, I know my total is 1, because 1 means that every possible option has happened. The probability that it's bruised is 0.054, so I go to bruised, and then it's 0.054. The probability that it's ripe and bruised, so that's ripe and bruised, is 0.019. Now I'm going to start filling in each row and column from there. So I just subtract, right? So I'm just going here, 1 minus that, okay, 1 minus 0.054 to fill in all of the blank spaces, 0.946. I can do that this direction too, because remember they have to add up to 1, and that gives me 0.88, and you can just check, 0.12 plus 0.88, that's 1. Then I can go across this way, 0.054 minus 0.019, 0.035, just keep going, 0.12 minus, that's right here, 0.019, 0.101, and lastly 0.88 minus 0.035, 0.845. So everything is filled in now. So if we want to see, are the events ripe and bruised independent, what would this mean? Well, it means that if an avocado is ripe, does it affect the percentage that are ripe? Will that affect the percentage that are bruised? If more of them are coming in ripe, is there a chance that more of them are going to be bruised? Or do these things have nothing to do with each other? We can find this out mathematically, and therefore we can actually use it to make determinations on things. So we want to first find what is the probability that an avocado is ripe given that it's bruised. We then also want to find what is just the probability that it's ripe. If these things are equal, then it's going to be independent. If they're not equal, then it's going to be dependent. So let's work it out now. The probability that it's ripe given that it's bruised. So again, you can find, there's two ways to do this. We can find ripe and bruised, which is 0.019 divided by the probability of bruised, which is 0.054. You can also do it from the table. The probability that it's ripe given that it's bruised. So I'm going into my bruised row. I'm only looking in there, and I'm saying what's the probability that it's ripe out of this. So you can also just do it straight from the table. We divide this. Okay, and we get 0.35185, and then the probability that it's ripe is 0.12. We just got that right from the table, and it was given to us. These are not equal, therefore these are dependent. And if you think about it, that makes sense, right? Because if they all come in and they're not ripe, they're probably not going to get bruised because they're harder. But if they're coming in and you have the probability really high that they're ripe, so there's a lot of them that are coming in soft and ripe, they're probably going to dent each other more, and more of them are going to get bruised. So it makes sense that the more ripe there are, the more bruised there would be. And therefore, these events affect each other, and that is dependent. That's what dependent means. So that's today's lesson. You're going to practice this, okay, just this. And then on Wednesday, we're going to do a handout where we